Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series. Today we are exploring chirality and the mirror world of molecules.
Thank you so much for having me. I am really excited to get into this one. It's a fascinating topic.
It really is. And I have to say, usually when we pick a subject from the sources, I expect it to sort of, stay in its lane.
Right?
Like if we're talking about astronomy, it stays in space. If we analyze it just completely refuses to be categorized.
It absolutely refuses.
Yeah, it's everywhere. It starts out as this basic geometry problem, literally just asking you to look at your hands, and then it spirals into a massive tragedy in medical history. And from there it turns into this profound mystery about the very origin of life on Earth, before finally ending up in the cutthroat patent courts of big pharmaceutical companies. It is a wild journey.
It's a fundamental property of the universe that sits right in front of our faces every single day. But we rarely ever notice it until it either miraculously saves a life or tragically ruins one. It's all about this concept of asymmetry in a world that we so desperately want to be neat and symmetrical.
Well, let's start right at the beginning. Section 1 of our notes focuses on the foundations, what we think we know. And we have to start with the concept of handedness.
Yes.
The sources actually give this deceptively simple instruction to start things off. They say, simply, look at your hands.
It sounds like a bizarre meditation exercise, doesn't it?
Yeah.
But it's actually this incredibly profound physics demonstration. So for everyone listening, if you just hold your hands up right now, palms facing towards you, what do you actually see?
Well, I see two things that look pretty much identical. I've got a thumb, 4 fingers, a palm on each. Same size, same general structure.
Yeah.
They are perfect mirror images of each other.
Exactly. If you were to put your left hand up to a mirror, the reflection looking back at you looks exactly like your physical right hand.
Yeah, that makes sense.
And here's the crucial physical test. Try to superimpose them. Try to put your left hand directly on top of your right hand with both palms facing down towards the floor.
Okay, I'm doing it now.
Yeah.
And yeah, it doesn't work at all.
Wow.
My thumbs are sticking out on completely opposite sides.
Yeah.
My pinkies are totally misaligned. It's just a clumsy mess.
Exactly. They are what we call non-superimposable. No matter how much you rotate that left hand or flip it around, as long as you keep it in normal three-dimensional space, you physically cannot make it occupy the exact same footprint as your right hand.
Right.
That specific property, being a non-superimposable mirror image, is what scientists call chirality.
Chirality. And the etymology here is just perfect. The word comes from the Greek word chair, which literally translates to hand.
It's the defining characteristic, handedness. And once you have the vocabulary for it, you honestly start seeing it everywhere in your house.
Oh, did.
Like, think about a screw. A screw is a chiral object. The metal threads spiral in a specific direction, either clockwise or counterclockwise. You physically cannot start a left-handed screw into a right-handed nut. It just won't engage. The geometry fights you.
Or think about your shoes. If you've ever tried to put a left shoe on a right foot in the dark.
Oh, it's terribly uncomfortable.
It is. It sort of fits, maybe, but it pinches your toes. It pushes in all the wrong places. It constricts you. That physical discomfort you feel when the wrong shoe is on the wrong foot. The sources suggest that is a macroscopic, everyday version of what happens at the microscopic molecular level when things go terribly wrong.
That's a great way to visualize it. Conversely, we also have objects that are acral. Acral meaning without hands.
Like a coffee mug.
Exactly, a standard coffee mug. Or a plain tennis ball.
Right, because if you look at a perfect sphere like a tennis ball in a mirror, the reflection is just
another identical tennis ball.
Right. You can rotate the real ball to match the reflection perfectly. It has a plane of symmetry right down the middle. So chirality is really all about the absolute absence of that symmetry.
Precisely. Now, this is pretty easy for us to grasp with physical, everyday objects. You can hold a shoe, you can hold a screw, but the material takes us down to the molecular level. And this is where, I admit, my brain had to do a little bit of spatial gymnastics. We are talking about microscopic molecules that actually have hands.
Chemists call these enantiomers.
Enantiomers, okay.
Right. To visualize this, I want you to imagine a central carbon atom.
Oh.
In chemistry, carbon is basically the ultimate building block, and it likes to form exactly 4 bonds with other things, like a little tripod with a stick pointing straight up.
Perfect geometry, yes. Now, if you attach 4 completely different things to that central carbon, let's say you attach a hydrogen atom, a chlorine atom, a methyl group, and maybe an ethyl group, The strict rules of 3D geometry dictate that there are two, and only two, distinct ways to arrange those four items in space.
And those two arrangements are mirror images of each other.
Exactly. You get a left-handed version of the molecule and a right-handed version. And just like your human hands, you cannot twist or bend one molecule to make it look perfectly like the other. They are entirely distinct physical entities.
And chemists obviously have a naming system for this, right? The notes mention an older system using D and L, but it says the modern standard is R and S.
Yeah, the modern standard is the Pon-Ingold Prelog system, if we want to be formal. It's a set of rules based on atomic priority. But the letters are what matter. R stands for rectus, which is Latin for right, and S stands for sinister, which is Latin for left.
I always found that fascinating. Sinister literally just means left. It really highlights how historical language and culture were just heavily biased against left-handed people from the very start. Like, oh, you write with your left hand. You must be inherently evil.
There's an absurd amount of cultural baggage packed into that one word, but in modern chemistry, it's stripped of the judgment. It's strictly a structural label for the 3D arrangement. But here is where this concept gets really, really tricky for people to intuitively grasp.
Okay, lay it on me.
If I were to give you a glass flask filled with the pure R molecule, the rectus one, and then I gave you a second glass flask filled with the pure S molecule, the sinister one, and you take them to a lab to check their boiling points.
They would be the same.
Completely identical down to the fraction of a degree.
What about the melting point?
Identical. How about their solubility in water? Identical. How dense are they? Identical. If you didn't know you were dealing with chiral molecules, you would swear on your life that they were the exact same chemical substance.
Ah, so this is the physical deception that the source material warns about. In a standard, neutral environment, these two molecules act like flawless, identical twins.
Precisely. In what we call an chiral environment, like just floating around in a simple test tube of pure water, they behave exactly the same way. Because water molecules don't have hands. Water doesn't care which version of the molecule it's bumping into.
Right.
But, and this is the massive world-changing but, biological systems are absolutely not neutral environments.
The human body is a chiral environment.
It is an intensely, overwhelmingly chiral environment. We are literally built out of chiral building blocks. Almost all the proteins in your muscles and organs are made exclusively of left-handed or L-amino acids. And the sugars that power us, they are D-sugars, right-handed. Even your DNA is a right-handed twisting helix. So our bodies aren't just simple glass beakers holding water. We are a complex, jagged landscape of very specific 3D shapes.
So to interact with that landscape, the drugs or nutrients we ingest have to match those shapes. The analogy the texts use all the time is the lock-and-key mechanism.
It's a classic analogy for a very good reason. Think of a cellular receptor in your body. Maybe it's a pain receptor in your nervous system or an enzyme inside a harmful bacteria. Think of that receptor as a lock. Because that lock is built out of those specific chiral proteins we just talked about, the lock itself has a shape. It is, say, a left-handed lock.
Okay, so the drug molecule we swallow is the key trying to open that lock.
Exactly. If you send in the correct enantiomer, which the medical field calls the eutomer, the good part, it fits the lock perfectly. It clicks right into the receptor, it turns the biological mechanism, and you get the desired effect. Your headache goes away.
But what if you send in the exact mirror image of that molecule, the distomer?
That is like trying to jam a right-handed key into a left-handed padlock. Best case scenario, it just doesn't fit at all. It bumps into the receptor, bounces off harmlessly, and gets flushed out of your system doing absolutely nothing.
That doesn't sound too bad, just inefficient. But what's the worst case scenario?
The worst case scenario is that the mirror image molecule actually fits perfectly into a completely different lock somewhere else in your body. A lock you definitely did not want to open. Or it jams the original lock halfway and permanently breaks the machinery. This is the exact moment where the difference between identical physical properties in a beaker and completely different biological properties in a human becomes a matter of life or death.
And we really cannot talk about this life or death difference without addressing the massive tragic shadow that hangs over this entire field of chemistry.
No, we can't.
The tragedy of thalidomide.
It is the defining moment. If you look at toxicology, pharmacology, and drug regulation, the history of those fields is strictly divided into two eras. Pre-thalidomide and post-thalidomide, which changed everything.
Let's really set the scene for people so they understand how this happened. We are talking about the late 1950s and early 1960s. This is the post-war economic boom, the era of better living through chemistry.
Exactly. There was this huge, almost blind optimism about pharmaceutical science. We had just conquered polio, antibiotics were changing the world, people trusted pills.
Right.
So a German pharmaceutical company named Grunenthal releases a new drug called thalidomide. It was aggressively marketed as an absolute miracle sedative. They said it was completely non-addictive. They said it was so safe you could give it to a child. And crucially, it was heavily prescribed as the ultimate cure for morning sickness in pregnant women.
And the notes here highly emphasize that they were manufacturing and selling this drug as a racemate. Can you break down what that term actually means for the listener?
Yes, this is critical. A racemate, or a racemic mixture, simply means it is a 50-50 mix. When you synthesize a complex chiral molecule from scratch in a chemical plant using standard, cheap industrial methods, you almost always produce equal amounts of the left-handed and right-handed versions simultaneously.
Because nature is very specific. But massive industrial lab chemistry is usually pretty messy.
Exactly. It's chaos. So every single thalidomide pill that rolled off the assembly line contained 50% of the R enantiomer and 50% of the S enantiomer.
And at the time, in the late 50s, nobody even thought to try and separate them.
Why would they? Like we established earlier, if you test them in a lab, they have the exact same melting point. They look like the exact same white powder. The prevailing assumption was simply that they would do the exact same thing in the human body.
But they absolutely didn't.
No, they didn't. The R enantiomer, the right-handed version, was indeed a highly effective sedative. It did exactly what it was advertised to do. It calmed the nerves and helped women sleep through the nausea. But the S enantiomer, the mirror image sitting right next to it in the pill, was a potent teratogen.
Teratogen, I looked that up. That actually translates from Greek to mean monster maker, doesn't it?
It does. It's a harsh word, but it describes a substance that causes severe physiological malformations in a developing embryo or fetus. Specifically, in this case, a condition called phocomelia.
Which is the profound shortening or absence of the limbs.
Yes. The long bones of the arms and the legs simply fail to grow in the womb. So you have thousands of babies being born with their hands attached almost directly to their shoulders like flippers, or their feet attached directly to their hips. It was an unprecedented humanitarian disaster. We are talking about 10,000 or more children across Europe, Canada, Australia, and other places whose lives were permanently altered.
And the actual mechanism of how this happens, which the sources say we only fully figured out relatively recently, is terrifyingly specific.
Yeah.
It's not just a general poison that destroys everything. It's a surgical, targeted attack on a specific cellular function.
It really is. It specifically targets a protein in the body called cereblon.
Cereblon. What does that normally do?
Cereblon is a key part of a cell's natural waste disposal system. It's part of the ubiquitin ligase complex. Basically, it acts like a molecular tagger that flags old or damaged proteins so the cellular trash compactor can destroy them.
Okay, so a garbage disposal system.
Right. But the S enantiomer of thalidomide happens to fit perfectly into a tiny pocket on the surface of the cereblon protein, like a missing puzzle piece snapping into place.
And when it snaps in, does it stop the trash compactor from working?
No, it's worse than that. It actually changes the physical shape of cereblon. It alters its surface just enough that cereblon suddenly starts grabbing onto proteins it is supposed to completely ignore.
Oh, no.
And one of those proteins it starts grabbing is a crucial transcription factor called SEL4. SEL4.
Yes. FAL4 is absolutely essential for the blueprint of limb development in a fetus. It tells the cells where to grow arms and legs. But thalidomide tricks the trash compactor into grabbing cell 4 and shredding it. It literally tricks the developing body into throwing away the very blueprint required to build limbs.
That is just, it's chilling. A microscopic change in geometry, just a molecule mirrored the other way, and the fundamental blueprint of a human being gets shredded by its own cells.
It's a sobering reality. But here is the massive twist to the thalidomide story, the twist that still haunts chemists who study this. You might logically ask, well, once they realized the left hand was evil and the right hand was good, why didn't they just separate the mixture? Why not just manufacture and sell the pure 100% safe R version?
Right. If they had just spent the money to purify it, would it have been a safe drug?
Tragically, no, it wouldn't have mattered. And this brings us to a terrifying biological concept called in vivo racemization.
In vivo meaning inside the living body. Exactly. The human body, particularly the liver, is an incredibly active and hostile chemical environment. It turns out if you take a pill of 100% pure R-thalidomide, the completely safe sedative version, and you swallow it, the enzymes and the slightly basic pH conditions inside your blood and liver will actually physically flip the molecule.
Why? It forcefully changes the chirality.
Yes, the body literally detaches a single hydrogen atom from the carbon center and then immediately reattaches it on the completely opposite side. It forces the molecule to mirror itself.
So the human body literally manufactures the poison out of the cure.
Precisely. Within just a few hours of swallowing a perfectly pure, safe pill, your blood would reach an equilibrium. You would have a 50-50 mix of the safe drug and the monster maker flowing through your veins again. You cannot stop the metabolic conversion.
Wow.
So even if the brilliant chemists back in the 1950s had been fully aware of chirality and had separated the drug perfectly, they likely still would have walked right into this disaster because they had no idea that the human body could perform metabolic flipping like that.
It really shows the sheer hubris of the time, thinking we can just throw these novel synthetic molecules into the incredibly complex, ancient machinery of life without fully understanding the user manual first.
It was a brutal wake-up call, and it permanently changed the regulatory manual. We have to mention the FDA here, specifically Dr. Frances Kelsey.
Yes, she's a legendary figure in American medicine.
She is a hero. She was a medical officer at the FDA, and despite immense pressure from the pharmaceutical companies, she adamantly refused to approve thalidomide for sale in the United States. She felt the safety data was incomplete, especially regarding nerve damage. Because of her stubbornness, the U.S. largely avoided the massive wave of birth defects seen in Europe, and after the truth came out, world governments realized they had to change everything. Now, you cannot just ignore the other hand of a molecule. If you submit a chiral drug for approval, you have to rigorously prove exactly what both enantiomers do.
And that leads us to some modern examples of how we handle this today. Let's look at something way less tragic: ibuprofen.
Yes, the Advil sitting right in your bathroom cabinet.
The sources point out that ibuprofen is also sold as a mixture, a racemate.
It is. Every standard pill of ibuprofen is exactly 50% S-ibuprofen and 50% R-ibuprofen.
But wait, we just spent the last 10 minutes talking about how terrible mixtures are and how strict the FDA is now.
Yeah.
Why is this allowed to be sold as a 50-50 mix?
Because sometimes we just get incredibly lucky with biology. In the specific case of ibuprofen, the S form is the highly active painkiller. It perfectly blocks the COX enzymes that cause inflammation in your body.
Okay, so what does the R form do?
The R form is biologically inactive in terms of pain relief. It doesn't fit the lock. But crucially, it also doesn't fit any dangerous locks. It doesn't cause birth defects. It doesn't cause toxicity. It's essentially just harmless filler.
So half of the pill I take for a headache is just dead weight.
You would think so, right? But remember that crazy liver trick we just talked about? In vivo racemization.
The flipping mechanism.
Yes. But in this case, the flip actually works totally in our favor. The human body takes the completely useless R-ibuprofen, and an enzyme called a racemase grabs it and performs a metabolic inversion. It literally flips the useless molecule into the useful S form.
That is basically a biological magic trick. Your body takes the chemical waste and actively recycles it into more medicine.
It's incredibly efficient. So you swallow 200 milligrams of a 50-50 mix, and eventually, thanks entirely to your liver doing the heavy lifting, almost all of that 200 milligrams becomes active painkiller over the next hour or two.
That's amazing. But then we have the opposite scenario with another common painkiller, naproxen, brand name Alev. The notes specifically highlight that this one is absolutely not a mixture.
No, not at all. Naproxen is manufactured and sold as a purely isolated single enantiomer, S-naproxen, 100% pure.
Why the drastic difference in how they make it compared to ibuprofen? They do the same thing, right?
They treat similar symptoms, yes, but the mirror image, the distomer of naproxen, isn't just a lazy, useless molecule waiting to be flipped. The R-enantiomer of naproxen is a potent liver toxin. It causes severe hepatic damage.
Oh, wow.
Yeah. We absolutely cannot rely on the body to flip it into the safe version fast enough before it causes permanent damage to the liver tissue. We simply cannot risk having the bad hand present in the pill at all. So pharmaceutical chemists have to do the incredibly hard, expensive work of separating the molecules in the factory before the drug ever gets shipped to the pharmacy.
It really just seems like a massive roll of the dice every time you synthesize a new chiral molecule. Sometimes the mirror image is your best friend. Sometimes it's just a neutral stranger passing by, and sometimes it's an absolute killer.
It is a chemical lottery, and managing that deep uncertainty is exactly why modern drug discovery is so completely obsessed with understanding chirality at a fundamental level. You have to know exactly which biological game you are playing before you put a chemical into a human being.
So that thoroughly covers the what and the how of our foundations. But now we're moving into section 2 of our discussion, the active debate. Because now we have to ask why. And honestly, reading through these sources, this is where the science gets almost philosophical.
Oh, without a doubt. We are diving into the mystery of biological homochirality.
Biological homochirality. I feel like that sounds like the title of a dense Robert Ludlum spy novel or something.
It does have that ring to it.
But let's break that down for the audience. Homochirality basically means same-handedness.
Right. Remember how we said that when you do chemistry in a standard lab setting, making molecules from scratch, you almost always end up with a 50-50 mix?
The racemate. Chaos prefers a mixture. Entropy wants things to be jumbled up and equal.
Exactly. Dead inorganic chemistry strongly prefers symmetry and mixture. But life is a total snob.
Life is incredibly exclusive.
Beyond exclusive. If you were to take a sample of the amino acids that make up the proteins in your own body, or the proteins in a giant blue whale, or an oak tree, or a microscopic bacteria living at the bottom of the ocean, they are all, without exception, L-amino acids. Left-handed. 100%.
There is no mix.
None. 0 right-handed amino acids in the structural proteins of life.
And what about the sugars?
The sugars that form the rigid backbone of your DNA and RNA molecules, they are all D sugars. Right-handed, 100%, across the entire biosphere of Earth.
Okay, this is the part that profoundly confuses me. Why? Why couldn't life just use a mixture? Or if it had to pick one to be efficient, why not pick the other way around? Why did nature explicitly choose left for the proteins and right for the genetic sugar?
Welcome to one of the single biggest unsolved mysteries in the study of the origin of life. Scientists call this problem symmetry breaking.
Symmetry breaking?
Yes. How exactly did we transition from a perfectly symmetrical, completely dead chemical universe to an intensely asymmetrical, wildly thriving, living biological system?
And the sources outline 3 major competing theories for how this happened. Let's walk through them one by one. First up on the list, the coin flip.
Yes, often referred to in the literature as the frozen accident theory. This essentially argues that the whole thing was just pure dumb chance.
Like life just booted up in some tiny volcanic pond a few billion years ago.
Exactly. Imagine a little warm primordial soup. You have basic amino acids forming through natural electrical storms and chemical reactions. Maybe just by sheer random statistical fluctuation, what physicists call Brownian motion, you ended up with a microscopic imbalance in that one specific puddle.
Like instead of a perfect 50-50 split, you had...
Let's say you had 1,001 left-handed molecules and exactly 1,000 right-handed molecules.
So an incredibly tiny difference. One single extra molecule.
Right. But because life is fundamentally a process that replicates and consumes resources...
the tiny advantage snowballs.
It gets permanently locked in. The first primitive proto-life forms that happened to use the left-handed molecules suddenly had a tiny bit more raw material available to them. So they ate the resources faster, they reproduced slightly faster, and the competing right-handed potential life essentially starved to death before it could ever really get going. It's a ruthless winner-takes-all scenario at the microscopic level.
So if we were to somehow rewind the tape of planetary evolution, wipe the slate clean and let it play out again, we might all be entirely made of right-handed amino acids right now.
According to the frozen accident theory, absolutely yes. We could have easily been the mirror people. Because fundamentally, there is no basic chemical reason why L-alanine works any better as a building block than D-alanine. They are chemically, functionally equivalent. It was just a cosmic coin toss.
But then, of course, there are the competing theories that argue, no, it wasn't a coin toss. The fix was in from the very start. And this leads us to the second theory, the extraterrestrial origin.
This is where the science gets truly cosmic. And we actually have hard physical evidence for this one, mostly from meteorites, specifically the famous Murchison meteorite.
This is the one that crashed down in Australia, right, in 1969.
That's the one. It's not just any rock. It is a carbonaceous chondrite, meaning it is a pristine relic from 4.6 billion years ago, forming at the very, very dawn of our solar system, before Earth even existed.
So it's basically a time capsule.
Precisely. And when astrochemists carefully ground up pieces from the deep interior of this meteorite and analyzed the chemicals inside, They found dozens of different amino acids that had formed purely abiologically, just floating in the cold vacuum of space dust.
But here's the kicker. It wasn't a 50-50 mix, was it?
It was not. To everyone's absolute shock, they consistently found a slight but measurable excess of L-amino acids, the left-handed ones.
So the bias towards the left already existed in the dust space before the Earth had even finished forming its crust.
That is the staggering implication. The cosmic seeds of life that eventually rained down on the early cooling oceans of Earth were already subtly tilted to the left.
But wait, how does a random dead rock floating in deep space acquire a chemical handedness? That seems impossible.
It's a great question. The leading astrophysical theory to explain this involves something called circularly polarized light.
Okay, we need to unpack that.
Sure. Imagine you are floating in a giant molecular cloud near a rapidly spinning neutron star, or a massive, chaotic star formation region. These incredible cosmic engines blast out intense ultraviolet light, but the light waves aren't just waving simply up and down or side to side. The magnetic fields twist the light so it actually spirals through space. It corkscrews.
So the light itself is chiral.
Exactly. The light itself has a handedness. And if that intense corkscrewing UV light bathes a cold dust cloud that happens to contain basic 50-50 racemic amino acids, that twisted light will physically interact differently with the left-handed molecules compared to the right-handed ones.
Really, light can do that?
Yeah. Yes, through a process called asymmetric photolysis, basically destruction by light. The corkscrew light might resonate just perfectly to shatter the chemical bonds of the right-handed molecules slightly faster than the left-handed ones.
So over the course of millions and millions of years,
the massive dust cloud is slowly, violently purified by this intense starlight. The right-handed building blocks are constantly degraded by radiation, while a slightly higher percentage of the left-handed stuff survives intact.
and then that purified dust eventually clumps together, condenses into a meteorite. The meteorite slams into the early Earth, and boom, it delivers a prepackaged cosmic bias for left-handed life.
It is incredibly poetic when you think about it. The reason we are composed of left-handed proteins today might literally be because a massive star exploded near our solar nebula 5 billion years ago and shone a twisting corkscrew light on the dust of our ancestors.
That connects biology and deep space astrophysics in such a beautiful, profound way.
Uh-huh.
But the sources say there is actually an even deeper level to this debate. The third theory, parity violation.
Ah, yes. This is the realm of pure fundamental physics.
Right.
So, for a very long time in physics, there was a deeply held belief in something called the conservation of parity. It was basically an assumption that the fundamental laws of physics are perfectly symmetrical, that the universe behaves exactly the same way in a mirror as it does in reality.
That seems like a solid logical assumption.
It was until the late 1950s. A brilliant physicist named Qian-Shun Wu conducted an experiment, often called the Wu experiment, that shocked the physics world. She proved that the weak nuclear force, the fundamental force responsible for radioactive beta decay in atoms, is absolutely not symmetrical.
Wait, the force itself has a handedness.
It does. When a radioactive nucleus undergoes beta decay and shoots out an electron, those emitted electrons have a heavily preferred quantum spin. They are, in a very weird quantum sense, left-handed. The universe has a built-in directional bias at the subatomic level.
But does a subatomic quantum spin actually affect wet, sloppy chemistry happening in a warm pond?
And that is the absolute bleeding edge of the debate. Some theoretical chemists and quantum physicists have run incredibly complex supercomputer models. And they calculate that because of this fundamental asymmetry in the weak nuclear force, the L-amino acid molecule is actually inherently ever so slightly more energetically stable than the D-amino acid.
Really? How slightly are we talking?
We are talking about an energy difference on the order of 10 to the power of minus 17 joules.
That is incomprehensibly small.
That is infinitesimally small. It's a ghost of a whisper of a fraction of a calorie.
So is that tiny whisper really enough to matter in the real world?
If you are doing an experiment in a glass flask over a weekend, no, it's totally negligible. But if you are applying that tiny, persistent bias across the entire staggering volume of a planetary ocean, churning constantly over the course of 1 billion years, maybe, just maybe, that relentless tiny nudge from the fundamental laws of physics provides the 0.0000001% advantage that eventually tips the scales and wins the biological war.
So, to summarize the debate, we are either the result of a lucky coin flip of chance or twisted starlight from our environment, or the inherent parity violation of fundamental physics itself.
Exactly. Those are the big three. But regardless of which one of those theories actually started the imbalance, you still hit a massive mathematical wall, the problem of amplification.
Right, because even if the starlight, or the weak force, gives you a 1% excess of left-handed molecules, how on earth do you get all the way to 100% purity?
Yes, life isn't 51% left, it's 100% left. You desperately need some kind of chemical amplifier.
And this brings us to what might be one of the coolest concepts buried in these sources: chiral amplification.
It's a brilliant piece of science. The notes specifically mention two huge breakthroughs here: the theoretical Frank model and the experimental SOI reaction.
Okay, let's start with the Frank model. Who was Frank?
Frederick Charles Frank was a British physicist. Back in 1953, he proposed a purely mathematical model to solve this exact problem. He asked, mathematically, how does a slight majority completely eradicate a minority? And he figured out you need two specific things to happen simultaneously. First, you need autocatalysis.
Photocatalysis, meaning the substance literally acts as a catalyst to build more of itself.
Right. The left-handed molecules actively help manufacture new left-handed molecules out of raw materials, and the right-handed ones help make more right-handed ones.
But that alone just keeps the ratio the same, just bigger.
Exactly. Autocatalysis alone isn't enough. You also desperately need the second element: mutual antagonism.
Mutual antagonism. That sounds like a polite term for chemical war.
That's exactly what it is. Frank proposed that if a left molecule randomly bumps into a right molecule in the soup, they bind together chemically, they form a useless stable dimer, and they essentially drop completely out of the active solution. They totally neutralize each other.
I see the math now. Okay, imagine you have a tiny puddle. You start with 51 active lefts and 49 active rights. They are churning around.
Yes.
The 49 rights crash into 49 lefts, neutralizing each other one for one in this mutual antagonism war. So the rights are now entirely extinct. They are gone.
They are wiped out, but you still have exactly two active lefts remaining in the puddle.
And because of the first rule out of catalysis, those two surviving lefts now have the entire puddle of raw materials all to themselves. They start manufacturing more lefts with absolutely zero competition.
You've got it. The math is elegant. It amplifies a microscopic initial imbalance into total 100% dominance. But for over 40 years, this was just a neat mathematical trick on a chalkboard. Nobody could prove it actually happened in real chemistry until a Japanese chemist named Kenso Sawai finally proved it in 1995.
The Sawai reaction.
Yes. He discovered a specific zinc-based organic reaction that perfectly followed Frank's rules. And the amplification power of this reaction was staggering. It was so hypersensitive that the reaction would swing to 100% purity based on almost nothing.
How sensitive.
If there were microscopic, almost unmeasurable handed impurities in the quartz glass of the beaker itself, that was enough to dictate the final chirality of the entire chemical batch.
That is wild. The glass decided the outcome.
It did. There was even a study showing that the physical direction you stirred the liquid, whether the vortex spun clockwise or counterclockwise, could sometimes tip the scales of the reaction.
Just from physical stirring. That perfectly segues into the other experiment mentioned here, the Viedma ripening, because that involves physical grinding.
Yes, the Eve crystal experiment. This is visually one of my favorites. A researcher named Cristobal Viedma took a saturated, sludgy liquid of sodium chlorate. Now, sodium chlorate forms solid crystals that have a specific handedness.
Okay.
He creates a flask filled with an exactly 50-50 mix of left-handed solid crystals and right-handed solid crystals swimming in the liquid. And he throws in a handful of little hard glass beads. And then he just puts the flask on a magnetic stirrer and lets it violently churn.
So the glass beads are just physically smashing the crystals to pieces.
Just constant, violent mechanical grinding. The solid crystals are constantly being smashed into powder, dissolving back into the liquid, and then recrystallizing. Smash, dissolve, grow. Over and over.
But how does that lead to purity?
Through a complex thermodynamic process known as Ostwald ripening. Essentially, in a chaotic environment where things are constantly breaking and reforming, larger crystals are more stable than smaller ones. If there is even a tiny microscopic imbalance, say one extra microscopic left crystal survives smash, it will draw dissolved material to itself slightly faster than the right crystals can.
So it's survival of the fittest applied to inanimate rocks.
Exactly. The majority crystals literally cannibalize the minority crystals through the liquid phase. Viedma found that if you just let the flask grind for a few days, you eventually look inside, and the entire beaker has magically converted into a single massive population of 100% left crystals. or 100% right crystals.
That feels like the ultimate missing link. You can easily imagine a scenario on early Earth where you have the twisted starlight giving you a tiny, tiny 1% nudge, and then you have the violent physical churning of ocean waves crashing against rocks in a tide pool, acting as the glass beads.
And suddenly, almost inevitably, you have an entirely homochiral chemical environment, perfectly prepped and ready for the complex machinery of life to boot up. It takes the origin of handedness out of the realm of pure magic and drops it firmly into the realm of comprehensible physical mechanics.
Fascinating. Absolutely
Great.
fascinating. Okay, so we spent a lot of time in the deep past looking at the origins, but now we need to pivot and look forward. We're moving to section 3, frontiers. Because, as the sources clearly show, humanity isn't content to just sit back and observe chirality anymore. We're aggressively trying to master it.
We are trying to build the mirror world ourselves. This is the intensely competitive field of asymmetric synthesis.
Right, making single-handed molecules on demand. Because as we saw with the thalidomide and naproxen stories, we really, really need to be able to make just one hand at a time.
It is arguably the most important technical challenge in modern pharmaceutical manufacturing. We know nature does it effortlessly. Biology uses giant, complex enzymes to build chiral molecules perfectly every single time.
Biology is the master craftsman.
It is. But human chemists really struggled for over a century. For a long time, the only way we could get a pure molecule was through a brute force method called resolution. We would intentionally make the 50-50 racemic mixture and then use complex, tedious chemical tricks to separate them and literally throw half the batch in the trash.
Which sounds incredibly inefficient and expensive.
Hugely wasteful. So the holy grail was to find a catalyst, a chemical tool that could force the reaction to only build the left hand or only the right hand from the very beginning.
And the notes break this down into the 3 pillars of catalysis. The first pillar is nature's tools, enzymes.
Right. We figured out how to harvest enzymes from bacteria and use them in vats. They work beautifully, they are incredibly precise, but they are also fragile. They only work under very specific temperatures and pH levels, and they usually only build one very specific molecule. They aren't versatile.
So chemists moved to the second pillar, metal complexes.
This was the heavy artillery of 20th century chemistry. Scientists discovered that complex structures containing rare, heavy transition metals like rhodium, ruthenium, or palladium could act as rigid 3D chiral templates.
So the metal acts like a physical mold.
Exactly. It holds the raw ingredients in a very specific rigid posture so they can only bond in one chiral direction. And this won Nobel Prizes. It was incredibly effective, but it has massive drawbacks.
Let me guess. Heavy metals are incredibly toxic.
Extremely toxic. If you are using ruthenium to catalyze a heart medication, you have to spend an absolute fortune purifying the final product because you cannot have even trace parts per billion of heavy metals left in the pill. Plus, these metals are incredibly expensive and environmentally damaging to mine.
Which perfectly sets the stage for the massive breakthrough. The third pillar. The one that actually won the Nobel Prize in Chemistry just recently, in 2021.
Yes. The Nobel went to Benjamin List and David Macmillan for the development of asymmetric organocatalysis.
Organocatalysis. Okay, break that word down for us.
It was a total paradigm shift. List and Macmillan essentially stepped back and asked a very bold question. Why are we relying on giant, fragile enzymes or toxic, expensive heavy metals? Can't we just use small, incredibly simple, cheap, organic molecules to do the exact same job?
And what kind of civil molecule did they use?
Which of the most famous examples Benjamin List worked with was simply proline.
Proline. Isn't that just a common amino acid?
It is. It's one of the basic building blocks of life. It's already chiral, it's cheap as dirt, and you can buy a bucket of it for nothing. List discovered that this tiny little proline molecule could act as a highly efficient asymmetric catalyst all by itself.
How does a tiny molecule do the job of a heavy metal template?
It acts like a highly aggressive molecular bouncer at a nightclub. The proline molecule temporarily binds to one of the raw ingredients, and because of its bulky chiral 3D shape, it physically blocks access to one entire side of the molecule.
Ah, I see.
It basically says, the left door is blocked. If you want to react, you have to come in through the right door. It dictates the geometry of the final product with astonishing precision.
That is elegant. And I imagine the impact of this is massive, right?
It's revolutionized the industry. Organocatalysis is dramatically greener, it's vastly cheaper, and it leaves behind zero toxic metal residue. It has effectively democratized chiral chemistry. Now, smaller labs or developing nations don't need $1 million worth of platinum to build complex, life-saving single enantiomer drugs. They can use simple organic compounds.
That is fantastic. But the frontiers mentioned in our sources aren't just strictly about manufacturing drugs.
Hmm.
There is a whole other section here about understanding fundamental energy transport, and it references something called the CISS effect.
Oh, this is mind-bending stuff. The CISS effect. CISS. It stands for chirality-induced spin selectivity.
That sounds like we're drifting back into quantum physics.
We absolutely are. This concept beautifully bridges the gap between squishy organic chemistry and hard quantum mechanics.
Okay, walk me through it.
So, traditionally, we usually just think of chirality as a static shape, like a physical left glove or a right glove.
Right, it's geometry.
But physicists recently discovered that chiral molecules actively interact with the quantum properties of electricity, specifically electron spin.
Okay, remind me. Electrons have a spin. They spin up or down.
Yes, in a quantum sense, electrons have an angular momentum that is either spin up or spin down. In a normal copper wire, if you shoot electricity through it, the current is a totally random mix of both up and down spins, half and half.
But what happens if you shoot an electric current through a chiral molecule, like, say, a twisting helix of DNA?
This is the crazy part. The chiral molecule acts as an aggressive quantum spin filter. As the electrons travel down the twisting corkscrew of the DNA, the geometry of the molecule strongly interacts with the electron's spin. It allows the spin-up electrons to cruise through the helix effortlessly with almost no resistance.
And spin down electrons.
They get scattered, they bounce off the walls, lose energy, and get blocked. The helix basically filters them out.
So a strand of DNA is essentially a quantum sorting machine for electricity.
Yes. And this has staggering implications. For one, it suggests that nature might be using chirality for a totally different reason than we thought. Maybe life didn't just choose a right-handed DNA helix for structural stability. Maybe it chose a chiral helix because it is the most incredibly efficient way to transport electrical energy across a cell without losing it to heat.
Wow. If biology is already doing that, can we copy it for our own technology?
Absolutely. This is the foundation of an emerging field called spintronics. Imagine replacing the incredibly hot, inefficient silicon chips in our computers with cool, self-assembling organic chiral molecules that route data using electron spin instead of raw voltage. It could lead to computers that are thousands of times faster and use practically no power.
That feels like pure science fiction, but the physics is real.
It's very real.
All right, before we leave the frontier section, the notes highlight one more incredibly compelling story, and it's actually a redemption arc for the darkest chapter we covered today.
The return of thalidomide.
Thalidomide is back. Are you serious?
It is back. The drug that caused so much global misery and completely rewrote the FDA rulebook is currently being prescribed right now to save lives.
How is that even possible? What are they using it for?
It is currently a frontline, highly effective treatment for two major illnesses, complications from leprosy, and a particularly nasty form of blood cancer called multiple myeloma.
But wait, is it actually safe now? Did they figure out how to stop the racemization in the liver?
No, the chemistry is exactly the same. It still flips in the body. It is absolutely still a teratogen.
So how can they possibly prescribe it?
Extreme, uncompromising regulation. It is heavily controlled under a specialized program called REMS, Risk Evaluation and Mitigation Strategy. It is walled off. Absolutely no pregnant women or women who might become pregnant can ever be near the drug. Patients have to take pregnancy tests, sign extensive waivers. It's highly monitored.
Okay, so the administrative walls are high. But scientifically, how does the drug that destroys limbs suddenly cure blood cancer?
This is where the story gets brilliant. The scientific redemption comes from finally understanding that exact horrible mechanism we talked about earlier. Cereblon.
Right, the trash compactor hijacker. Thalidomide binds to cereblon and forces it to shred the limb blueprint protein, SAL4.
Exactly. For decades, scientists just saw that as a tragedy. But a few brilliant researchers recently looked at that exact mechanism and realized something profound. They said, wait a minute. If the thalidomide molecule has the power to completely hijack a cell's trash compactor and force it to destroy a specific protein, could we intentionally reprogram it to destroy a cancer protein instead?
Oh my God, they decided to weaponize a hijacker.
Precisely. And this launched an explosive new frontier in pharmacology known as PROTACs. PROTACs. It stands for proteolysis targeting chimeras.
What does a PROTAC actually look like?
Informally, we call them molecular glues. Imagine a molecule that looks like a microscopic dumbbell.
Okay, two ends connected by a string.
Right. One end of the dumbbell is essentially just a piece of thalidomide. Its only job is to firmly grab hold of the cereblon trash compactor. The other end of the dumbbell is custom designed by chemists to be a perfect key for a specific disease-causing protein, let's say a protein that is driving a tumor to grow.
So the molecule floats into the cell.
It grabs the tumor protein with one hand, it grabs the trash compactor with the other hand, and it literally glues them together. It drags the disease directly into the shredder.
That is just staggering. It deletes the disease from the cell entirely.
It completely revolutionizes how we treat illnesses. For decades, traditional drugs just tried to block bad proteins by sitting on top of them, like sticking gum in a keyhole. But PROTACs don't block the protein, they assassinate it. And it was all made possible by taking the horrific molecular mechanism of a tragedy, understanding its exact chiral geometry, and turning it into a programmable tool for precision medicine.
That is the ultimate lesson in Know Thy Enemy. Wow. Well, as amazing as the science is, we eventually have to land this plane back in the messy real world.
Unfortunately, yes.
We are moving into the final section. Section 4, implications, ethics, economics, society. Because whenever you have groundbreaking new chemistry and life-saving drugs and massive patents, you inevitably have brutal economics.
You certainly do. And the central economic phenomenon discussed in the sources is something known in the industry as the chiral switch.
The chiral switch. It sounds like a skateboarding trick, but the notes make it clear this is a highly aggressive corporate strategy.
A very, very lucrative one. To understand the chiral switch, you have to put yourself in the shoes of a CEO at a massive pharmaceutical company. Let's create a hypothetical scenario.
Okay, I'm the CEO.
You have a flagship blockbuster drug on the market. Let's call it Drug X. It treats millions of people, it's beloved, and it earns your company billions of dollars a year. But you have a massive problem. Your 20-year patent on Drug X is about to expire in 6 months.
Oh, yeah, the dreaded patent cliff.
Exactly.
Yeah.
The moment that patent dies, a dozen generic manufacturers are going to flood the market with cheap knockoffs. The price of Drug X will collapse by 90%, and your stock price is going to tank.
Yeah.
You are sweating. But you realize something. The original Drug X that you patented 20 years ago was formulated as a racemate. It's a 50-50 mixture of 2 enantiomers.
Okay, so I call my lead chemist.
You march down to the lab and you say, listen up. I need you to quickly isolate the active enantiomer from Drug X. Just the eutomer, the good half. Throw the other half away, purify it perfectly, and run some quick clinical trials to prove it still works.
Why would I do that?
Because legally, according to the patent office, a 100% pure single enantiomer is classified as a distinct, novel chemical entity compared to the old 50-50 mixture.
Oh, so I can patent it again.
Bingo. You immediately file a brand new ironclad patent for the pure version. You rebrand it, maybe you give it a snappy new name like Drug X Plus. And the brilliant, devious part is the timing. You aggressively launch this new premium drug right before the old patent expires.
So I launch a massive marketing campaign targeting doctors.
Exactly. You buy the ads, you send the reps to the clinics, you tell the doctors, hey, don't prescribe the old dirty mixture anymore. That's old technology. Prescribe our new, perfectly pure, scientifically refined Drug X Plus. It's cleaner, it's better.
And so all the doctors switch their patients over to my new patented drug, right as the cheap generic version of the old drug hits the market. So the generic companies get stuck trying to sell a product that everyone suddenly thinks is obsolete.
It is a ruthless defensive maneuver. And it works perfectly. You keep your market share, you keep your high prices, and you extend your monopoly for another 10 or 15 years.
But the massive multi-billion-dollar question is the new pure drug actually any better for the patient?
And that is the absolute core of the controversy. The sources highlight the most famous real-world example of this, the battle of Prilosec versus Nexium.
The purple pill. Everyone remembers those commercials.
Exactly. Prilosec, generically known as omeprazole, was a massive seller for severe heartburn and acid reflux, and it was a racemate mixture. As the Prilosec patent was approaching its death, the manufacturer, AstraZeneca, executed a flawless chiral switch. They isolated just the pure S-isomer of omeprazole, patented it, and launched it under the brand name Nexium.
So Nexium is literally just one half of Prilosec.
Literally just the left half.
So was Nexium medically superior? Did it cure heartburn better than the old generic pill?
The clinical data was aggressively subtle, let's say. It wasn't a totally fake improvement. Because it was pure, Nexium was metabolized by the liver slightly slower than the mixture, which meant a slightly higher concentration of the drug stayed in the bloodstream for a slightly longer time.
Okay, so it offered a marginal, tiny improvement in long-term acid control.
Very marginal. The critics, and there were many, pointed out that if you simply told patients to take a slightly higher dose of the dirt-cheap generic Prilosec, you achieve the exact same clinical result.
Really?
Yeah, but because of the massive, brilliant marketing machine and creating what lawyers call patent thickets, Nexium became an absolute blockbuster, earning billions and effectively delaying cheap generic competition for years.
So the critics call this evergreening.
Evergreening. You keep the patent green and fresh by making tiny, scientifically trivial tweaks to the molecule without actually inventing anything meaningfully new. It's seen by many as a manipulation of the system.
But wait, the sources also point out that sometimes a chiral switch is incredibly valid and medically necessary.
Absolutely. It's not all corporate cynicism.
Okay.
Let's look at another famous case. The antidepressants citalopram, sold as Celexa, versus escitalopram, sold as Lexapro.
I've definitely heard of both of those.
Celexa was the original 50-50 racemic mixture, but clinical researchers discovered something fascinating. In this specific case, the bad enantiomer in the mixture wasn't just harmless deadweight. It was actually actively interfering with the good enantiomer.
Like they were fighting over the same receptor.
Exactly. The bad hand was partially jamming the lock, preventing the good hand from getting in and doing its job of regulating serotonin.
So in that scenario, removing the bad half isn't just a patent trick. It actively unlocks the full potential of the drug.
Exactly. When they purified it and released Lexapro, which is just the pure S-enantiomer, they found that it was significantly more effective at treating depression, it worked at a much lower milligram dose, and crucially, it had fewer side effects for the patients.
That is a completely legitimate, vital medical reason to execute a chiral switch.
It is, and that duality is what creates this incredible, agonizing tension in the global healthcare system. On one hand, from a purely scientific standpoint, pure single enantiomer drugs are undeniably more elegant. They are cleaner. Why on earth should we force a patient's liver to process 50% absolute chemical waste if we don't have to?
Right. In a perfect utopian world, every single pill in the pharmacy would be a perfectly pure single enantiomer.
It's objectively safer.
But we don't live in a perfect world. We live in a world with budgets.
Mm-hmm.
If the old, slightly messy racemic generic costs 10 cents a pill and the newly patented, highly pure enantiomer costs $10 a pill.
It forces hospital administrators and insurance companies and governments to make agonizing choices. Is that marginal 5% improvement in safety or efficacy actually worth spending billions of extra dollars in limited healthcare funding? Funding that could go to entirely new research. It is an ethical and economic tug of war that we are constantly losing and winning simultaneously.
And the really ironic part of all of this, according to the notes, is that this entire economic tug of war is actually the direct result of the thalidomide tragedy.
It is all connected. We talked about how the FDA reacted to thalidomide. In 1992, they issued a landmark policy statement. They basically said to the pharmaceutical industry, if you want to sell a racemic mixture, you must exhaustively characterize the biological properties of both individual enantiomers.
Which is incredibly expensive and difficult to do.
Extremely expensive. And the FDA added, however, if you just bring us the pure single enantiomer, the regulatory pathway is much, much faster.
Like unintended consequences.
Exactly. The FDA's primary goal was purely safety. They wanted to prevent another monster maker. But by writing the rules that way, they completely accidentally created the perfect regulatory and legal roadmap for the massive multi-billion-dollar chiral switch business model.
Unintended consequences all the way down the line. It really shows how every decision in this field ripples outward.
It does.
Well, as we close the file on this topic, I want to try and distill what we've actually learned here. We started by looking at our own physical hands. We zoomed down into the atomic structure of carbon. We talked about the heartbreaking devastation of the 1950s. We went up into deep space to look at twisted starlight. And we ended up sitting in corporate boardrooms arguing about patents.
It is a massive scope.
So for you, as an expert looking at all these sources, what is the ultimate takeaway for the listener? What should we hold on to?
For me, the most profound takeaway from all of this research is the realization that the universe is fundamentally not neutral.
Not neutral.
Right. We tend to naturally assume that space and geometry and basic chemistry are just these passive blank symmetrical canvases, but they aren't. At the deepest subatomic level and the highest biological level, there is a preference. There's a bias.
It's like the universe has a personality.
It really is. Life itself looked at the mirror and actively chose a side. It chose left for the proteins that build our muscles
Yeah.
and right for the sugars that hold our genetic code. And that ancient cosmic choice ripples through literally everything we experience today, even something as simple as the smell of breakfast.
Wait, smell. Does chirality affect how things...
Oh, absolutely. The notes mention this briefly, and it's brilliant. Take the chemical molecule limone.
Limone, okay.
It's a chiral molecule. If you synthesize the R-isomer, the right-handed version,
Yeah.
and you sniff it, your brain registers the distinct sweet smell of fresh oranges.
Okay.
But if you synthesize the S-isomer, the exact mirror image, and sniff it, it smells completely different. It smells like harsh lemons or pine turpentine.
Are you serious? The exact same atoms, just mirrored, and it changes an orange into a lemon.
Yes, because the olfactory receptors deep inside your nose are chiral locks. Your brain knows the physical difference between the left hand and the right hand of that molecule, and it interprets them as entirely different experiences.
That is absolutely wild to think about.
So literally, from the smell of your morning fruit to the profound mystery of how the first cell formed, to the incredibly complex engineered drugs that might one day cure cancer. We are all walking, breathing inhabitants of a deeply asymmetrical mirror world, and we are only just now beginning to learn how to navigate our own reflection.
What an incredible thought to end on, a deeply asymmetrical mirror world. Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us on Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.